Welcome back, everybody. So this is part 2 of how to fast boot your Raspberry Pi Zero into a bare metal mode. I've been through the background of why I'm trying to do this in the last piece. I mean, basically we're trying to get a Pi up and running as quickly as possible to minimize uptimes, which in turn will minimize battery usages, so extend lifetimes. There's an argument about whether this is the most sensible way of doing things, but you know, what the hey, we're having fun. So this is going to be all about how we grab code, build it up, get it onto a Pi, boot. Hopefully that will happen quite quickly, and then we're going to try and find some sensors on an I2C bus on this lovely little Enviro Plus shield on top of this Raspberry Pi Zero. And I think if we can do that, which is by no means a given, then we'll call that a win for this session. So here goes. First thing is we need to have Gcc Compiler installed. You see this here, it's pretty standard stuff. OM, non, EABI. I won't go into this. You can Google for how to install this. You can download the package itself from OM and set up and off you go. So you need that compiler installed. I think that's essentially really your only dependency for this. Then we need to go and grab the really nice open source Circle project that these people have put together. So let's git clone that from their repo. Off we go, we're there, so we got the code now. Then going back to the instructions, and this is why I love well-documented open source projects. You know, you just think of something to do and some really clever people have done all the hard work and have hopefully written down how to copy them, and people like me can come along and just push buttons, which is absolutely fantastic. So you got some defaults you got to set up. Luckily for us, these settings are standard for the Raspberry Pi Zero. So we're going to leave them as they are, and then we're going to do what we're told and run make all clean, like so. With the dot prefix, because we like to have known environments to work within, so that's set us up into the state that we want to be. And then if we run the make all command with a bit of luck, that's going to kick off and it's going to start building up the this Circle bare metal coding framework for the Pi. It seems to be working, so that's fantastic. As I said to you in the last piece, I mean, this looks to be, I mean, I'm just encountering this now. I'm no expert and I'm guessing a lot of things, so don't believe me. Go and ask these people. They did the work, but it looks to me fantastic. I mean, they've got all sorts of component support for the Raspberry Pi system on a chip device. You know, they've got GPIO support, I2C support, UARTs, display, Ethernet. Really nice. Feels like a really good thing to be using. So that's built now, and it looks to have built a kernel image of about 170K. You know, if you compare that to where we are nowadays with a lot of embedded Linux kernel images and then distributions, you can see that we're quite small compared to gigabytes of file system to be written onto SD cards. So the other thing that we need to do if we look at the instructions is we need to go into the boot directory where they have some setup there. We need to run make, and what that does is going off into the nether regions of the interwebs to pull down the Raspberry Pi boot files, boot code, because we need some of that to be able to get the Pi up and running. Now you probably know the way this stuff works is it's quite sort of standard in IoT nowadays, and they've got an in-ROM bootloader, which is what runs in the chip when you power the Raspberry Pi, and then that does a bit of setup and that goes off and it loads in a second stage bootloader, which can come from different places, but for the purposes of what we're doing, it loads in a file from SD card. It runs that, I discovered yesterday, on the GPU, I think, or some such thing, which is all very, very interesting. I don't really understand that, but whatever. It runs a second stage bootloader, does some more setup, and then it loads some optional bits and pieces and loads in a kernel image. So as far as we're concerned, there's going to be some sort of standard stuff that gets loaded in as a part of this boot process that will result in loading a kernel image file. And what we're doing is we're building our bare metal code into that kernel image file, and instead of running you know and love the embedded Linux boot that leads on to whatever, shells, desktops, applications, we're just going to run our stuff. So hopefully that should be a little bit faster. And if you've managed to put up with me talking to this point, we've managed to get all that boot code downloaded, which is lovely. So now what we're going to do is we're going to go and choose one of these rather nice little sample applications that these folks have given to us. There's like a wealth of stuff to do. I really don't know where to begin, but keeping on track, because we're trying to do the environmental sensor stuff, I want to run this number 32 I2C shell, and what that's going to let us do is to just interact and scan for sensor IDs on an I2C bus, which maybe I'll talk about a little bit later. So there's a kind of a harness main application here, which I had a look at, and basically it initializes up, the kernel, whatever that might be, the core of this framework, I guess, and then it goes off and it sort of runs that, and it catches some exit conditions, and that looks just like a very basic text harness, which lets us get into the custom bit of what we're doing, which is here. Now looking at the initialization of this, it looks pretty cool, because it looks as though it's sort of setting up things like screens and timers and loggers and USB and all kind of things that look like they might be of some use to us. And when we go through this initialization, we can see it's setting up interrupts, and then the screen, serial port, other bits and pieces through to USB and our console. And that's interesting, because what it means is that I might, say I want to really optimize this boot process. Maybe I don't want to initialize screen output over a display. I'm not going to have one in a Beehive. So it looks as though I can sort of take things out, which again might be able to improve performance in the future, but that's a discussion for another time. So what we're going to do is we're going to build up this particular example, which is going to give us a particular custom kernel.image. And then I'm just going to remind myself what we need to do to get the files onto the SD card, if I can find that. Right, so basically it says copy the Raspberry Pi firmware from the boot directory with your custom kernel.image. So let's try this then. What I'm going to do is take my SD card out of my Raspberry Pi, which I've already done actually. Wow, it's the Blue Peter, isn't it? Here's one I prepared earlier. And I've got my little adapter, you know this stuff. This is how you sort of blow things onto SD cards, micro SD cards for Raspberry Pi. So I'm going to put that in the SD card reader in the side of the computer, and if I have a look at that, then I should have that mounted. I've got that mounted in media AGLN 4 and some hex digits, and there's nothing in there at the moment, nothing up my sleeves. There's nothing on here. This is an empty card. For those who care, it's formatted with a single partition as VFAT FAT32, which is basically the standard way things get formatted. If you stick a new SD card into a computer and it says format, then that's what it's going to do on a Windows system. If you know Linux, you're going to know how to do this anyway, aren't you? So there we go. So that's our card. It's quite a big card, 32 gig, but you really don't need that amount of size. So if I look in my boot folder, where am I again? Let's remind myself. Okay, so I'm here. So what I'm going to do is copy my kernel image over to the SD card. That's done. And then I'm going to go into my boot directory, and I'm going to copy my second stage bootloader, bootcode.bin, over to where I want it to be. And I'm going to copy, let's go with these start, I can't remember which start file it is. I think it's start.elf is the one that we want, over to, excuse me, the file window sync, which persists data to storage, always very important to do, if you don't want to lose data. And then I'm going to unmount the drive. Boom, done. So I can take that out now, and I can put this into my little Raspberry Pi system, making sure that it's not powered. And now, with a bit of luck, that's going to boot up and it's going to run this I2C code. So let's see if we can sort of figure out how to get that going. I've got the HDMI output of, you can sort of see the way they do it on the Pi Zeros. You've got a little mini HDMI to standard HDMI here. And that's plugged into something that we discovered a few months ago, a few years ago actually now. I mean, COVID's making everything a blur. But it's called a mirror box, right? It's a mirror box, which is gorgeous little box, where it's basically like it takes HDMI input from a system, and then it looks like a video capture device on your computer. So instead of having to kind of lug around monitors from A to B, you can just take that box and it will kind of pipe your output from any HDMI capable system into your computer, and you can do stuff. So it's kind of neat. So what we're going to do is see if we can get that mirror box up and running and going. And I've got some text on the screen from a previous boot. What I'm going to do is to power the Raspberry Pi with our new code build on it. I'm going to do that. 3, 2, 1. Got to get the connector around the right way. 3, 2, 1 now. And if we are lucky enough, we see the boot, the rainbow screen for the boot, and now the code is running, and we're now in our shell. There you go. It's pretty fast, eh? Now I reckon that we can disable a lot of stuff in there as well. We can take out that, if we don't need a display, then we don't need any of that HDMI display stuff. So we should be able to boot even faster. But you can see from what I'm showing you that we're really pretty quick now. So next thing is I've got a keyboard plugged into the Raspberry Pi Zero, and remember that this keyboard is being supported by that bare metal framework now through USB, and that, if you know about these things, that gives you a bit of an idea. It's a pretty mature framework, and so I'm sort of tappity-tapping on this thing, and I'm on I2C bus 1, which I think is the bus that we've got the Enviro Plus I2C sensors on. Now if we go back to our browser display, I just want to show you over on the Enviro Plus here. Here, lovely little bit of kit, for what you get, cheap at the price. I actually made a mistake and I got the kind of lower priced version of this, which doesn't have all the gubbins on it. We've got the full fat one in the Hive, but I've got a little unit to demo with here which hasn't got everything on. But what it has got on, if we look at the spec sheets, so if we look here, there's a few different sensors. There's BME 280, which gives us temperature, pressure, humidity, LTR 559, light and proximity, and then there's a bunch of other stuff. What we're going to look at, just because we're somewhat time limited, aren't we? We're going to look at the LTR 559. The LTR 559, here is the data sheet for that device, and what I'm looking for at the minute is every I2C device comes up as its own particular address on the I2C bus, and that's how you can have multiple ones chained off each other off the bus. And I'm just trying to see if I can see in here where that address is, and there we go. As if by magic, the address is 23 hex on the I2C bus. So what I want to do is I want to scan in my circle bare metal I2C shell to see if I can find that. How are we going to do that? The way they do it here is to do a detect. So let's do a detect. And oh my word, isn't that fantastic? Love it when that happens. So we've got a 23, which is the LTR part, I'm going to 76, which if memory serves, I think is the BME part that we talked about, but I'm not certain about that. Anyway, so now what we want to do is to talk to this 23 part and see if we can just get some sense out of it. Now, you know, we got these unfortunate, people have been talking about that, haven't they? We've got an unfortunate kind of master-slave terminology that's been used in the industry, certainly since before I started work, and I'm going to try not to use that. If I do, my apologies. It's a slip, you know, I'm a work in progress. So what we're going to do is use that command to set the node or the device that we want to talk to. What have I done? I got that wrong. Let's go back there. So we're going to type that in for that node, and we're going to go to address 23 because that's what we want to talk to. And then if we go back to our browser, you see in our browser that we've, I'm just going to move that up here so that you can see a little bit easier. Yeah. You know, any data sheet worth its salt has a set of register definitions for these parts in it. This is no exception. For the LTR part, you normally find with I2C parts that they've got one or more registers that have got like a hard-coded number in, and that's how you find out what you're talking to, because you know you've got a part at an address. You can kind of assume what kind of part it is, but it doesn't necessarily mean it is what you think it is. So if you've got a kind of a better kind of part, then what you're going to find is that you've got some kind of IDs in there that you can interrogate to double check that you're really talking to what you want to be talking to. And indeed, on this part, if we look at these registers here, we've got an 86 hex and an 87 hex. Excuse me, and that's going to give us a part ID, which should be a 92, and it's going to give us a manufacturer ID, which is going to be a 05. So if we get those out, we know that we're talking to this LTR part on the Enviro Plus, on the I2C bus of the Raspberry Pi. Let's try it. So 86 is the register that we want to be talking to. We've already, yeah, I need to switch you back over to see that. We've already set the node that we want to talk to as being 23. So now let's write, oh, let me just double check what I'm doing here. Now let's write 86 register, which basically is how you talk to these things. Right, I want to talk to the information in 86. And then you read a couple of bytes. Oh my word again. It's fantastic, isn't it? I make it look so easy, don't I? I know, I don't know. I've done about like 5 of these takes. It's not they've not worked. This is good. Anyway, so we read a couple of bytes back, and you can see that we've got the first of those IDs. We got the 92, which is our part ID, and because we read the following byte, that comes out of the following register on I2C. We've got a 5 back, and that 5 is our manufacturer ID. So we have been able to build up our bare metal framework, build up a custom sample application to talk over an I2C bus to environmental sensors, get them onto an SD card simply by copying 3 files, boot that up really quickly, and then talk to these sensors and get some information out of them. So let's just try that again. Let me just show you. If I power down the device, the Raspberry Pi, and then 3, 2, 1, power up, and we get the display, and then we are executing code. And at this point, we could be running our own stuff, essentially. So, you know, that really, I think, gives a good idea that it is possible to fast boot a Raspberry Pi. We can run our own custom code as a kind of vastly overpowered microcontroller, and I think that's going to work quite well for my battery-powered scenario. Now what I'd like to do next is to look at customizing some of this code, optimizing it to, you know, probably take out the display initialization and see just how fast we can boot up, get some readings out, temperature, pressure, humidity, say, squirt them out so that I can capture them with this device I'm talking about that's going to do the turning on and turning off, the comms, turn it off again. And that will begin to give us an idea of the current consumption, the power consumption, which we can then look at against a battery in terms of its milliamp hours availability, and that tells us how long we can run a system in the field for. And that's going to be quite interesting. So I don't know when I'll get around to doing that, but if you want me to ask, and more people ask, the more likely I am to do it, and have a great afternoon. Thanks for bearing with me. Oh, and I'll say, if you want to talk to me, I'm on @embedded_IoT on Twitter. It's the best place to catch me. Thanks again.